All right, so I've just now started recording, and I'm going to give a brief example or an explanation on how QuickSort works. And so this is the idea of QuickSort. QuickSort is very effective if you have a very large list of data. So let's pretend that this is an unsorted set of many, many items, thousands and thousands of items. QuickSort works using a partitioning algorithm recursively. In other words, it recurses and it partitions and then recurses. So if you remember the details on recursion, recursion breaks problems up into smaller, identically structured sub-problems until the problem is obvious. And that's what QuickSort does. It's recursive. And here's how it works. It has a base case, and that base case is the following. If there's only one spot left, then that spot by definition is sorted. If you have the number 5, it's not out of order. It's just there. So that's when QuickSort stops, whenever it reaches an array size, a partition size of 1, then it's done. Or 0. 0 means there's nothing there and there's nothing to sort. That can also be true. If you pass it an array of no elements, it will simply say, I'm done. In order to get to that size, we've got to cause the array to get smaller and smaller. And so this is what QuickSort does. It pulls out an element in the list. It doesn't matter which element it is. The easiest one to get is the first one, but sometimes people will grab from the middle to try to get a better partition. But if the list is randomly sorted, then it doesn't really matter which one you pick. Let's take a simple one and pull the item out of the middle. So what we do with this item is we take it out, right? And this is what's called our pivot point. Pivot, P-I-V-O-T, pivot. Whatever the heck that number is, we don't know, all right? But it is now no longer in the list, or I should say, there's an empty space in the list. It actually stores this number still, but because we've copied it out, we can erase it from the list or overwrite it without losing it because it's sitting off to the side. This is similar to insertion sort. With insertion sort, you pull the item out, you shift everything to make a gap for it, and then you insert it back in. That's how insertion sort works. Well, you pull the item out so that when you scoot the item over, there's room. So we've pulled this item out, and now our list has one empty space in it. It's not actually empty, but it's good enough. And what we do is we run an algorithm called a partitioning algorithm. There are at least 2 of these that I know of, but I'm sure there are more than 2. The partitioning algorithm gets the entire item, the entire list, uses this empty space and partitions the list into 3 different spaces. As it partitions, it moves items that are smaller than the pivot to the left, items that are greater than the pivot to the right, and items that are equal to the pivot, it doesn't matter, one side or the other. And what you wind up with as it does this is all the items that are smaller on the left, all the items that are greater are on the right, and the pivot point winds up exactly where it belongs. So after the partition, the pivot point will be wherever it is supposed to be. And so it will be inserted into that spot, and all these items are less than, all these items are greater than, and what we have now is a sublist, the pivot where it belongs, and a sublist. Because we now have two sublists, we have made a recursive maneuver here because we have two smaller, identically structured sub-problems. And so what we do then is, knowing that this item is in the right space, a correct spot, we get this one and we do the same thing. We pull a pivot point out, we partition it, and then we have two smaller sublists, and then we get one of those sublists and we pick a pivot point, and we just keep doing this, and the sublists get smaller and smaller and smaller until they base case. And when they base case, when this whole side has been reduced to 0 size items or one size 1 subarrays, then all of them will be in place, or they won't matter because there's not even a thing there. What the result is this entire half of the array is sorted. And then we move over to this one and we start splitting it using pivot points, reducing it to tiny 0 or 1 size arrays. And then when those are done, it scoots back up and gets the larger partitions, and it eventually finishes. So it has elements of backtracking in it, if that makes sense. Okay, does everybody understand how QuickSort works? Are there any questions? You can use your emote at the bottom to give me a thumb up, a reaction, to give me a thumb up if you understand. If you don't, then ask a question in the chat. Okay, so I'm going to stop the recording. That's the basic idea of QuickSort. Remember, it's a recursive 3-step procedure. You pick a pivot point, you partition, right? This creates sublists. You check your base cases on the sublists and repeat. Okay, so I'm going to stop recording now.